Hello guys, and here we have a room which we call optics lab, right? I think some of you, or maybe all of you, have already been in the chemistry lab, right? You've been. So you have seen how we make nanomaterials, right? The quantum dots. Those are just examples of what we can make. Can anyone tell me what is the difference between quantum dots or nanomaterial? Is it the same stuff or not?
It's a subcategory of materials.
Yes, and if you put it simply, all quantum dots are nanomaterials, right? But not nanomaterial is a quantum dot, right? There should be special condition to get the quantum confinement. So here we have perovskite nanocrystals, and we have mercury telluride quantum dots. Here we have some organic molecule, and we have some simple solvent. So when you see they're all different by color, right? So can anyone tell me why the color is different?
The band gap is different.
Yes, everything absorbs. Even so, you see for those two guys, they have a band gap, right? They're semiconductors. Those two guys doesn't have because this is a simple solvent, right? It's organic. In this as well. So it has a homolumal levels, but anyway. So the thing is, everything absorbs. Even this guy, which is transparent by our eye and doesn't have any color, it absorbs. You can see the spectrum here, right? This is gray line, and it's flat completely, especially in the visible range, right? I put here for you from 300 to 3000, and our eye, human eye, can see only, I think, from 400 to 700. So we can see by eye only this small part. And for example, this solvent, it starts to absorb in the ultraviolet, but we cannot see it. So by eye, it is transparent and without any color. This guy, it's organic dye, rhodamine, so it has a pinkish color, right? And it absorbs a lot in the visible range. We are able to see the color. This is perovskite sample which were prepared by eye. It has a yellow-greenish one, and you can see very sharp peak here, right? So it absorbs, and the less it transmits, and again I see the color. So this guy is mercury telluride quantum dots, and we cannot see it. I would say it's brownish, right? Black brownish, because this guy absorbs everything in the visible range and started to transmit only, in the infrared. So this is completely black to our eye, right? Yeah. If I increase it, right? If I change the range, so you can see those visible guys more clearly, right? So the purpose of this spectrum which I show you, when we made our material in the optics, in the chemistry lab, we can characterize it by eye, right? But it's not enough. We are scientists. Makes no sense. By eye, we can see that is it stable, is it good or not. If by color, we can estimate the particle size, right? Is it acceptable? But just estimate if you know your sample. If not, we have to use a special equipment. And for example, this spectrometer will give us the precise optical spectrum, right? By this, we can say that those perovskite samples, those nanocrystal, has an excitonic feature at 490, right? It's very well defined, so we can judge by this. And after we dealt with absorption, we may want to know about how it's emit. So here in this lab, we do mostly materials which emit light or absorbs light, right? For example, perovskites are very good emitters, and if I take the blue light LED by eye, I can also tell, right, that it emits light. So, for example, mercury telluride, it's also emit light. It will absorb this blue light and will emit, but our eye cannot see it. With the visible stuff, it's easier. This organic rhodamine also, you see it's pinkish, but when I shine a light on it, it becomes yellowish. So here for the solvent it's just a scattering of the light. It doesn't emit anything because it cannot absorb in this range. So again, we characterize it by eye. By eye, I can see that this is green emission. What to do if I want to have a number? Number is more important in science, right? So if I want to get a number, I take this sample. First, I characterize this. I already did, right? This absorption, and I know where is the exciting feature. I know where this material absorbs the most efficiently. Then I go to the spectrometer. This big thing, we call it photoluminescence spectrometer, and it has a xenon lamp over there. It's very super intense, right? 150 watts, so it's closed. You cannot see it by eye. It will harm your eyes. So then it has a monochromator. What is monochromator? It's a thing, right? A system which define the certain wavelengths. Mono means single, and chromic means wave, right? Of color. So if I open it, and just to demonstrate, right, what monochromator actually do. For example, I can open it. No, I can't. Oh yes. So I told the diffraction gradient to move at a certain position and to show me blue color. I know that it will be around 450, and you can look inside. It defined exactly blue color. If I'm not happy with the blue color, right, I can make it green, and now it's green. It's very easy. I can make it yellow. So this is very raw, you know, switching between them. Maybe what our eye can see. Red one. Right? The main purpose of this big spectrometer to do it on very precise level, right? So now, right now I open this lid, so you know, very large, but usually we use it at very small value. So the wavelength is defined very precisely. Even by eye, we will not be able to define the difference. By this we can. So just to obtain my spectrum, I already know where this material will absorb. So I would like to put 450, for example. I have to reduce the slit because it's very, very intense. Right? And I have to close the lid to protect my eyes and the detector. So I press apply. Time. And you see on the emission we already get some numbers, right, which means nothing for us yet. But if I tell it to measure the spectrum, I can define the maximum of the emission, not by eye but precisely, and the width. So basically everything what I need.
So the y-axis is the count of the photons, right?
Yes, exactly. So the brighter it emits, right, the more counts you have here, if I put it very simply, right? It also depends on how it absorbs and the efficiency of the emission. But anyway, so here we obtained the spectrum, already two spectra, right, if we count the absorption of our material which we prepared. And this is relevant for basically every material which we have in this lab, right? Some of them emits in the blue range. This is PL in the blue range. We cannot see by eye. By eye it will be like a bluish, maybe. And this one is, what is it, yellowish, I think, same like this, but different material. And this is infrared, which again we cannot see by eye, but I show you this mercury telluride sample. So this is the purpose of working in this lab, right? when we want to know more about our material. Then you see, this is quite fundamental features, right? Fundamental absorption and emission, but we are not limited with it. And if we want to know more about our material, for example, which kind of organic molecules is inside our solution, or just to prove something or disprove, do we have some residuals, we can use FTIR machine, which we also have here. Come. So I cannot open it for you, right? But if you ever heard about this machine, it works using the interference principle. And here you can see the signal, so it's interferogram. And I can show you the one of the most simple operational pathway. For example, I even will not take any sample, just to demonstrate you how universal is this technique. So here, if we use the spectrometer, we usually use visible light, right, or infrared, and we define it precisely. Here, we shine the whole black body light, so it's a very, very broad band. It starts from 1 micron, maybe 800, and it's spanned until 20 micron, so it's super broad band. And this light, this energy is enough to excite the movement of the molecules inside any materials, right? Any materials have these molecules inside, right? Atoms. So, for example, I took a simple piece of paper, honestly, and I want to know, is it a piece of paper, right? Because paper can be different from each other. Yes. All papers are different. Oh, I want to know, maybe it's plastic.
It's nature paper.
Yes, exactly. And I see some, spikes. What is it? So, if I know my material, I can tell this is carbon and oxygen vibrations, right? This is carbon and hydrogen, and somewhere here, no, this is maybe OH bonds, and someone here should be carbon and oxygen, whatever. If I know my material. If not, so I should wait patiently while it will collect, right? 23, 24. So you see, it doesn't absorb anything, right, in the certain range, but then it starts when the energy is enough to excite these vibrations. It's fine. Then I press simply search, and the program, it has a special library, right, and it gives me some hints. What is it? Right? Is it paper, or is it dextrose, or is it cellulose? And we can do the same with any material, like I don't know, polypropylene, even with our nanoparticles. If I drop our nanoparticles just right here on the diamond crystal, right, and the light will go here, so I will be able to investigate which organic species I have inside my nanocrystals. So this works for all organics, sometimes inorganics, which we have inside the sample. So when we prepare a sample, when we characterize it by means of optical spectroscopy, like absorption or FTIR or PL, we think what we do with it afterwards, and mostly we do devices. For example, I read with a specialist on the LED, light emitting diodes, right? I can make photo detectors. So if we go over there, right? So for example, I made this sample of mercury telluride, not exactly this, but similar. It's black and dirty. And I have this kind of substrate, which we call field effect transistor, right? So here you see silicon, and you see the gold electrodes. We call it drain and source. By eye, it's very hard to see. So this is just large, piece of gold for convenience to apply the bias voltage. The most important part is here. It's the device part, and basically here, these electrodes and here they meet together, and they look like fingers, like this. They overlap, and the device area is just a small area here, right? So if I want to taste photo detection properties, I can take my device and I can take quickly. So for example, I already preset here 1 volts of bias voltage, right? And I have my device connected. I want to apply it between drain and source electrode, so I press start. And you see it shows some current, dark current, because right now, so this material is sensitive to the light, but not so sensitive to this white light, which we can see. It's mostly infrared or something. So it shows some current, but if I will be bold and I shine on it, you see the small difference. Small difference, right?
Yes.
This we call photo detector. If I try to shine red light, maybe it's not enough. So blue light is better, right? It's higher energy. So this is we call the photo detector. The light is shining on it and creates additional photons, right? And those additional charge carriers, and they create a photocurrent, right? So this is dark current, which flows just because it's under bias. And if we shine light, we see photocurrent. This is the purpose of our work. So this sample is a bit tight, I would say. So also, just to define, right, good sample from bad sample, before to spend my time on the measurements, I can simply use optical microscope to take a look. It's the good sample of bad sample. So here I put a substrate, and each of you can, take a look on these binoculars, and you will see 2 devices. So upper one, so right now by eye you cannot tell. It's all the same, right? 2 devices all the same. But if you look here, you will see. So one of them will be perfect field, and another one will be quite not good, I would say, like this. So you can take a look. Usually before to. So if it's here, just right here. Oh, I see. Yes, you can touch it.
It's like lines.
Yes. So those lines are the fingers which I just showed you, right? It's very hard to see by eye, but if you see, if you look at the binocular, the top one is nice and perfect, and the bottom one is not good because it was already shown. So this is how I can check my devices before I spend my time.
What's the name of that device?
It's a photo detector. Very similar to what I just showed you. You can adjust the focus here.
So we need that to calculate the intensity of color.
No, we need to calculate the intensity of the photocard. Right? Yes. So we use spectrometers to evaluate its absorption initial properties, and mostly fluorescence spectrometer to evaluate how efficiently it emits. Right? We can measure quantum yield, right? To get a number. For example, if it absorbs 2 photons, okay, let's say 100 photons, right? 100. And if the sample emits 100, then quantum yield will be 1, right? Very, very efficient. Everything what was absorbed, it's emitted. But if it emits just 50, or maybe 2, that means that most of your energy was dissipated somewhere, lost, And we can think how to improve the sample. This is why we need this optical spectroscopy, right? This is just, microscope is just very simple. We can use it for more advanced studies, but most of the time we use it just to check out the sample. This is more or less it. How we do this is